All right, team. Today we're going to venture into mapping, talking about the basics of maps, what a map is, how we make them, what's a good map, what's not a good map. And we will also start working on, in ArcGIS Pro, just some basics of using the software. I don't know if we'll get to mapping today in ArcGIS Pro. We'll talk about symbology as well. Okay, let's start looking at some maps. So we'll start off with an interesting map. Which state is your least favorite?
I feel bad for saying this, but I gotta go with Texas.
But what is this map communicating? So is Texas our least favorite? Is it our most favorite? Is Oregon our least favorite, or Tennessee? Or Wyoming? Just kidding. Yeah, we don't know anything. We don't know anything about this. I think we can all guess what's going on here. No offense. I know you've got family in Texas. Yeah. Oh, I thought you did. I thought you had some connection to Texas. Why would I
See, only with one. Same here.
So Justin just disavowed himself from all his Texan family. I don't know where I got that from. How about this map? Yeah, the color scheme maybe is a little troublesome.
At least there's a legend this time.
We have a legend. What's going on with the legend? Does that feel intuitive to you?
No, because more than 50 is also great. I don't know. It's gonna be. It's just like so more than 20 is also. More than 30. So more than
Yeah.
20 is more than 20.
Yeah, the legend doesn't make any sense. What about the color scheme? Do you think that communicates what you would expect to communicate?
I feel like maybe it should be switched.
Yeah.
So that white is blank, so it's like
Low.
lower
Yeah.
density or whatever.
From an intuitive standpoint, darker colors means more, right? Or greater, or denser, or something like that. So there's kind of an intuitive sense, or an intuition we have with colors and shades, right? There's a darker shade typically means more. So there's a rules of thumb, best practices for communicating data. And there's a lot of ways we can communicate data looking at symbology. We can have graduated colors. So these are graduated colors, right? They're not necessarily the same shade or same color, but they go from light to dark. We can have proportional sizes. So here's an example of proportional. So we could have dots representing city centers, and then the population is represented by the size of the dot. Same with thickness of lines. And then here's that graduated color scheme. So this would be counties, people per square mile, like population density. So you can imagine a county map of Colorado, and darker colors would be higher population density, lighter colors would be lower. If we switch those colors, that might be a little confusing. What kind of symbology are we looking at here? What would be the name of the symbology? So we're looking at flood intensity. Here's the legend right here, flood intensity. Zach, how would you classify that symbology? Yeah, so you can bring them together, right? There's definitely something, you can do overkill with symbology, right? At the same time, you can make things work together. So in this case, we have proportional sizes, so greater flood intensity. which I have defined here as the peak discharge at a gauge divided by the average peaks of that gauge. So we get bigger circles, and I also made them darker and different colors. So I tried to do a little bit of everything to really make the more intense stream gauges pop out.
And also not overshadow the ones that are close in proximity that are.
Yeah, because this is an arbitrary delineation between, or demarcation between values, 2 to 4, 4 to 10. Where you put that line, that break in the categories, needs to you need to have a good reason for that. And if I were to make, I chose to make 4 as an important threshold. There's some literature based on that. So everything above 4 was purple. So they were kind of grouped together, and everything below 4 was blue or gray. I made these gray because I didn't want to overwhelm the map. You can see there's a lot of gray dots everywhere, and it would have been really noisy. It's already pretty noisy, right? Because I've got these boundaries, these kind of areas that I group them with. So, you know, there's always a balance between communicating data with symbology and making things too noisy, cluttered, hard to understand. I would not call this a perfect map. I think, you know, I'm trying to communicate a lot of things here. So maybe taking these boundaries out and the labels just to communicate the geography of flood intensity would clean it up quite a bit. Yeah, so we kind of think of when we show data, we have to do due diligence. We have to be doing a good job of not trying to sway people's interpretations of the data in a way that might be arbitrary or biased. So we have to have, you know, science and best practice based ways for doing that. Let's look at this map. What do we think? Internet users per 100 people. Yeah.
Makes it look like there's a big lake
Yeah.
there.
We're not going from like dark.
Right. It's all over the place.
Yeah.
Yeah.
You really have to pay attention to scale to understand.
Yeah. And so you're like, okay, is purple good or not good, whatever, more or less, is red more or less, like you don't know, it's not intuitive. In a color scheme like this, maybe there's a use for this kind of color scheme, but it wouldn't be this graduated from low to high. When you go from low to high, you want to have this graduated color scheme, light to dark, essentially. That typically makes the most sense. There's also, you know, you could have, I don't know, green or yellow to green to blue or something like that. So this is a little random. And also, like, we don't have data, I'm assuming, for some of these countries here. And I don't know, maybe that is a C, but if we don't have data, then maybe we need to have that in the legend. Maybe they need to be grayed out or something like that, because that's confusing, right? Yeah, that's a great question, and we'll get to explore some of that in the activities. ArcGIS has a lot of different ways of slicing a continuous data series up. So you could do it by, for example, quantiles. So you could say, okay, I want to have even quantiles at 10% of observations. So every, you know, increasing 10% of observations, I'm going to do a break. So that's like kind of a statistical method. You can do it by standard deviations. So here's my spread of data, and you know, here's the standard deviation of the data. So I'm going to split it up by that. You could just pick, you know, 0 to 1 or 0 to 10, 10 to 20, right? So there's a number of ways to do it, and you kind of have to think about how your data is spread statistically. Is it evenly distributed? So then maybe it makes sense to do equal intervals, or does it look like a bell curve? And maybe it makes sense to do standard deviations in that case, so that you have kind of equal amounts of observations in each bin. There we go. How's that look? little more intuitive. That's a little different. What do we think about this?
Let's lump in the middle grade in with the no data.
Yeah, you know, you kind of like, yeah,
Sorta
exactly.
See the difference? It's like an off white and a white.
Yeah.
Tells me something's important about.
Yeah, right. You might, maybe there's a, yeah, I don't know about that choice, but it's definitely really separating the low from the high. And is that important or not? I don't know. So this could be useful, but again, you have that trouble with the white in the middle and then the no data. How about this? Look at that legend now. What's that? Someone made this for teaching purposes. only. This is WHO did a worldwide study, cost $20 million. So does this color scheme work or not?
It kind of does, just because there's not really a relationship of more or less in the data. It's just like different categories. So I think maybe that works in the same way that you would just paint countries different colors. Just arbitrary.
Yeah, sardines is not less than sausage, unless you really hate sardines. You know, you got to try them before you don't knock them before you try it.
Papa John's has one.
Papa John's does?
Yeah.
Wow.
So you got to eat them when it's real hot, just like
You do
Jesus
not want cold sardines.
said. No, as soon as it starts to get like even cooled down a little bit, then it's like.
From the can. Yeah, like on cracker and cheese or
Or no, I'm thinking of anchovies.
something. Oh,
That's
right.
what Papa John's has.
Anchovies are the salty ones. Sardines are just like the fish in a can.
Oh, you're right.
Yeah. Yeah. Yeah, I mean, I would argue that this works because there's no natural ramp here, low to high gradation. So would I choose this colors? I don't know, maybe not, but the fact that it's just categories, it's just categorical data and not graduated data, then we can choose sort of a random color scheme and that's okay. Granted, we want it to be visually appealing and maybe these are a suite of colors that are not. I don't feel that strongly about it, but I think it's better than this. So we got to kind of think a little bit about symbology, but let's talk bigger picture. What is a map? What makes a map a map? And is this a map right here? What kind of information is on this image, we'll call it? So we kind of think, I mean, we see Google Earth, right? So we assume it's some satellite image. But do we know anything? What kind of information would be helpful on this?
Scale.
Right? Are we looking at a microchip? Or are we looking at a county-sized area?
But I can imagine it maybe is like fields with different crops or something.
Right.
County road labels.
Yeah, some road labels, some orientation. Where are we in space? So maybe a little inset map that says we're in this country, right? And here's a little area for reference. Yeah, so a map is certainly visual information, an image of an area, geographic area. But to give it context, we need a scale. We need a north arrow typically, maybe some kind of description or some kind of orientation so that the user can look at this and then quickly and intuitively understand what's happening and why we want to continue it. So when you think about reading maps, maps typically come with text, some kind of information to orient the user, the viewer. Visualization is obviously the most important thing, but we also need some good information. Where did the data come from? kind of a little caption or title that tells us who made the map, what's the affiliation, where did it come from. Being able to understand what data is being mapped. Is this data source valid? Is this a reasonable data source? Is it some fake data set that people made up for the pizza preferences of the globe? By visualizing, by presenting data visually, that creates meaning, right? And so if we look at a map that has random colors, but it's a graduated scale, it's not really meaningful to us. And we have to spend a lot of time going back and forth to really understand that. And so that comes down to our color scheme, scales, legends, breakpoints, meaning how we divide the data up into that symbology. All those things are important decisions that communicate information in a map. And it's important to be able to distinguish between data, what we want to communicate, and then visual fluff. So just excess symbology or things that aren't helping tell the story that you want to tell. So not everything on a map is going to be data necessarily, but maybe we have other visual elements that help make it look nice or orient the user to where things are and provide context. And then I think this is the last point, be aware of what the map is saying and showing and what might be missing. And that's kind of checking the color scheme, checking the legend. What are we showing and what are we not showing? And are the data being presented in a way that's reasonable? Let's take a little deeper look into geospatial data. We introduced this concept last time. So spatial data, geospatial data has obviously spatial component to it, X, Y points, vectors, polygons, lines, rasters, as well as attribute data, which is kind of a database attached to that. So those two things come together to make geospatial data. So let's look at some examples. Here's a little table we have. And I'm assuming the top one says value stolen. So we had maybe a car break-in, and this is a database of what cars were broken into and what's the value of what was stolen from them. What would be at the bottom table? What kind of information's in that? Yeah, someone went out and took some data. So pH and well, so maybe they went down and took a water sample of a particular well. Now, here's the attribute table, right? This is just the basic data. There's nothing spatial here, but we can add spatial data. So here's the address where the robbery occurred. And here is the latitude, longitude, and elevation of these particular wells. So now with this table, we can create a geospatial data set. We can, ArcGIS is able to read in addresses and give you latitude, longitude, or a coordinate based on that, based on kind of a national database of addresses. And then of course, latitude, longitude can allow us to plot these points on a map. So spatial data tells you where something is located, but not what it is. And then the attribute data tells you what something is, but not where it's located. And the way GIS works is here's polygons representing townships in a New England area. And I don't know if anyone's lived in New England, but they have counties and then they have townships. And so everything's divided up into little towns. And sometimes you pay town tax, county tax, state tax, and federal tax. It's brutal. But they have great services. So if we were to have this GIS data set, these polygons, and say we were to click on this and get some information, it would be linked to this attribute table that has the population, the area, maybe some other census type of information. And so the geospatial information system, the GIS, stores the links between the spatial data and the attribute data. And when we get into looking at geospatial data in general, we'll see that there's a lot of files involved. So if I call this a shape file or a feature, there's different ways of referring to this. There's actually going to be the shape file, which has the vector data, the geospatial data in it. And then there's going to be a database connected to it. And then there's going to be a projection file. There's going to be at least 4 files that make this geospatial data together, and they're all linked. So some data are better in a map form or a chart form. And what do you think is better in this case? So we have here's a kind of random data set. So the amount of federal funds that 24 states lost by refusing to expand Medicaid. So here are the states that did not expand Medicaid back when Obamacare was passed. Gosh, a long time ago. And here is the funds that the federal government would have given to support Medicaid expansion. So we see this as a table. And this is interesting. I mean, certainly you can pick out which states are losing a lot of money, which states aren't losing a lot of money. Maybe this would be a little more helpful if it were normalized by population or something like that. So you can compare. Certainly Wyoming, we know 500,000. Are you guys at 600,000 yet?
I think maybe. But we're still the least populated, and Denver still has more than us. I'm a Colorado. No, I don't know why I keep identifying.
Well,
but
yeah, I just whatever.
Stomping grounds.
Justin's from Texas. You're from Wyoming. Like, it's fine. Maybe that's why. I don't know. I'll stop saying that, I promise. So, you know, a chart is interesting, but a map maybe is a little more helpful just to kind of see how it's geographically spread. I wouldn't say that one is super important versus the other. What do you all think?
I'm kind of leaning towards the chart just because there's a lot of states that are relevant.
Right, that aren't part of the data set.
Yeah, but then maybe that's helpful to see on the map too, because then you can see regionally, like,
Yeah,
kind of what people are tending to do.
Right.
States are tending to do.
the South, the Southeast, the Midwest. Yeah, I can go both ways. And also, like, this is just gross money, billions of dollars. And like I said, you could display this different ways, proportionally speaking. Maybe it'd be same, I don't know, but billions of dollars per 100,000 people or something like that. You could divide it and normalize it. That's why, like, when we report COVID-19 numbers, it's usually cases per 100,000, because of course Denver is going to have more cases or more people than Mesa County, for example. Let's talk a little bit more about types of data. We have nominal, and that just means name, right? So names, labels, IDs. We have categorical data. And you can think of categorical data as, certainly there's going to be a name associated with it. And the example here is types of roads. So we can have a street, county road, a highway, an interstate, something like that. But you could imagine that for each category, you could just have a code associated with it. 1, 2, 3, 4. So that's the difference between categorical and nominal. Nominal, you need the information, you need the zip code, you need the address, the name, something like that. But categorical, it could be both. It could be a name, but underneath that is typically a code. Ordinal is very similar to categorical. Ordinal has a direction. So the order matters. So we go from high, medium to low, A, B, C, 1, 2, 3. It's still categorical, but it's the order matters. And so if you think about, we go back to the road example, we have small roads all the way up to interstates. And so that would be an ordinal type of classification. And then finally, we have numeric. And remember, what are the two kinds of numbers we can have in our data?
Continuous and discrete.
Continuous and discrete. If we have discrete 1, 2, 3, that's integers, that would be akin to ordinal data because it matters, the order matters. We go big numbers versus little numbers are important. They're not just random categories labels. So numeric is, we're typically going to be referring to that as decimal points, continuous data. So looking at this geologic map of South Dakota, what kind of data do you think is represented in these polygons with different colors?
Hard to say, but I guess geology.
So geology, right? Geologic units. And how would we, what would that look like in the database attached to this, Edgar? That's okay. So if we look at this data, and these are polygons, and they're representing geologic units, so sandstone, shale, whatever. What would the database that's linked to this GIS data look like? What would be the type of data stored in that database? Yeah, categorical. Because there's not like schist comes before shale, right? It doesn't matter. So we would just have names. You could also have nominal too. It could be nominal. Nominal meaning just a name. Categorical could be schist is 1, shale is 2, but the order doesn't matter. Yeah. So I would say, like, I mean, whatever. This is kind of semantics, but yeah, you could just have an attribute table with names, and you're good, and it's just linking the names. You just have to spell it right if you want to do some kind of correlation between things or some kind of analysis. But you could also have codes underneath that. So yeah. All right, so looking at this, we have type of flood across the state. What kind of data do we have here? What do you think, Justin? Yeah, categorical. Nominal, categorical. Yeah. Good job. So most of the floods in Colorado are from rain. We do have some snowmelt floods. More and more we're getting wildfire floods. Every now and then we get a little dam break. That's exciting. There was a bunch of avalanche that brought a bunch of wood down in that area, and they were worried that there would have been. It didn't. Oh, so it made a dam. The avalanche made a dam with wood, and they were worried that the whole thing was going to blow. But it was porous enough that it wasn't that big of a deal. Yeah, good memory. All right, let's talk about how we categorize data. And here's the same data set. So this is the average farm size in the US in terms of acres. So if you have a farm, how big is that farm? And there are, in this case, 6 different ways to categorize that data. So Jenks, this is an algorithm that they use to find natural breaks in the data. I don't actually know how it works, but it's one way to do it. And it kind of basically finds groups of data and puts breaks in between those groups. Equal interval just says, okay, we're going to go from high to low and divide that into equal intervals. Defined interval is, well, this is kind of weird. The legend's kind of hard to read. I want to just do it by thousands. So I'm going to go 84 to 1,000, 2,000, 3,000, etc. Quantiles, that says, okay, let's look at the distribution of data. And for every, in this case, we have 1, 2, 3, 4, 5 groups. I'm going to divide everything up and bin them so that I have an equal percentage of my observations in each bin. Does that make sense? So say I have 1,000 observations or 1,000 data points, then each of these 1, 2, 3, 4, 5 bins is going to have 200 observations in them. So that you're grouping the data together equally. If I did just the equal interval, I might have a ton of data in some of these bins and a very little data in some other bins. And so it's just a way to make sure you're representing the data equally. But does that make sense for this particular map? I don't know. Geometric interval. So this, instead of equal interval, this is arithmetic. Geometric it's basically like a log scale. And maybe you want a log scale because you have such a huge range of observations. You go from 0 all the way to 1,000,000. You don't want to do equal intervals there, right? And then finally, we have standard deviation. And this, you can see that the number scale is different because it says, okay, here's our middle values, 1/2 to 1.5 standard deviations, less than negative 0.5, and then greater than 2.5. So if you've got kind of like a bell curve type of data, maybe you want to look at the histogram and decide how you want to splice and dice the data. But it's interesting how, for example, the standard deviation, you can see obviously there's a really big distinction between the Southwest and Midwest and then the East here, which it doesn't pop out in some of these other types of ways. And so maybe if you don't know what the best way is, you try some of these, and maybe you have to study the data a little bit to understand how you want to present it. Mapping matters, and how you define your intervals matters. So let's take a look at these two maps. This is Georgia, COVID-19 numbers, July 2020, and then July 2nd, and then July 22nd. What changes between these two maps? Obviously, the cases change, but what changes regarding to the content of the map or the format of the map? They changed the scale. So we originally had red starting at 2,900, and you could look at this scale and be like, oh, they just did equal intervals, right? Something like that. Because, well, no, it's not equal intervals. It's some type of interval, but it's really hard to know what that interval is. And then they changed the scale. So now the red, which is obviously a really important visual communication tool, red really stands out against blue. The threshold changed from 2,900 now to 3,300. And so some states that might be in this dark blue would have been red over here, now they're not. So they're kind of moving the bar, right?
We also have different dates between the two.
What is
The first thing I noticed was on the far left, on the right map, there's 3 counties touching each other, and the threshold starts at 3,300 for the red. But on the left, the middle one isn't covered, even though there's a lower threshold. And so I was like, that doesn't make sense. And I was like, why is that? And then I saw that the dates were different. So
oh yeah, well that was the point. So this is a real map from Georgia's public health department. So in July 2nd, this was their map, and then July 22nd, 20 days later, they changed the way they show colors. And so if you were to compare one map to another to say, how is COVID doing in Georgia? You wouldn't think there was a big difference, but maybe there was a big difference, right? And so they're kind of obfuscating or hiding that changes by changing the color scheme. Maybe it was not intentional. When you bring data into ARC and say you're like, okay, give me quantiles, right? It's going to automatically do that. And if all of a sudden my data range changed, and you can see that now their data range went up to 5,400 cases per 100,000, it was 4,600. So it went up by 800, and it could have just been some automatic thing. You have to be really intentional with ARC because it'll do a lot of automatic stuff for you. And if you want to compare maps from one point to another, you have to go back in and do some manual things to make sure that everything lines up. So now they changed their color scheme, and you can go back and do the same map. So they have now graduated colors, so not categories or ordinal, I guess, ordinal numbers. And they made sure that their scale, they got some GIS guru here, because this is a little more sophisticated. And now their scale is consistent from month to month or week to week. And anything greater than 930 cases per 100,000 is saturated. So it's this dark kind of burgundy color. So now if we look at all these maps together, here's the July 2nd, and here's the July 22nd. And you can see that maybe you're not so worried about what's going on in Georgia between these two maps, but here it tells a much different story, right? So one of the things we can do to compare data across vastly different types of situations, you'll notice that this data is cases per 100,000. So that's called normalization, right? We divided by 100,000 so that we can compare the kind of density of COVID cases. Here's a map, says number of farms per state. Here's the absolute value of farms, and here's farms per square mile. And you can see that when we normalize, we get a much different picture. Texas has a ton of farms, but if you normalize, sorry, Texas, you're not the best. Some of these actually have a lot more farms per square mile than some other states. So there's no right answer for this. Well, in some cases, there is a right answer. I think looking at COVID cases and dividing by 100,000 per 100,000 makes sense so we can compare across counties. In this particular question, the number of farms, it just depends on what you want to know, right? So yeah, did you have a question? Yeah, okay, that's okay. Just working on a thumbnail. Hey man, I finally clipped my nails this morning. I couldn't find my nail clippers for like 2 weeks. Yeah. So, oh, right. Yeah. So per square mile. So obviously when we have some really large states with large land masses, that's going to it's going to be a bigger denominator. Here's another look, number of vacant homes.
Is that for township or
County.
county? I see Sheridan County.
You're still from
It
Wyoming.
looks like a tiny baby Montana.
Get some big counties over here. So here's number of vacant homes. Here's number of vacant homes per 100,000 people. Which one do you think makes more sense to communicate? If you think about kind of resources, where does a county care to do something about this? You know, encourage home ownership, or, you know, try to get people into vacant homes. Maybe a population standpoint, because how much money do you have to do that? If you look at this is, I don't know what county this is, somewhere in California. Obviously, there's a lot of vacant homes there, But if you look at the number of people that live there, it kind of washes out compared to some of these other counties. Here is annual precipitation averages. So that's interesting. Would we normalize this or not? And if you did, how would you normalize it? Right, I guess you could say like on average, here is the amount of rainfall we get in a given year. So I'd say it's not normalized. You can normalize it by area. That would be a way to do it. But do we need to normalize? Well, maybe if we want to say what happens, so if this is the average, right? And we talked about this in hydrology, that's normal, the climate normals, which is the average over the last 30 years. Maybe we would say, what is the percent of precipitation we got last year compared to average? That would be a normalization. So the average in Grand Junction is 9 inches of rain. And what do we get last year? And so what percentage, right? So that would be a way to normalize if we wanted to. But in this case, it's just having absolute values is helpful. I don't like that color scheme. And then I think this is the last little bit here. So solar potential, meaning what's the potential for generating solar energy? So this is discretized by state. And we're talking about resolution now. By county. And then just by a grid. So this is just a raster. Because we know kind of cloudiness, the solar index is basically a value that we can do. So depending on the resolution, we can have much different information. And where is this important? Well, does a state want to invest resources into solar energy? Maybe they want to know at the state level. But if you can get this high resolution data, maybe you're a homeowner and you want to know what your solar potential is.
And also, I think in combination with population, because like in Washington State, it's showing that it's good, but most of their population is out by Seattle, I think.
Right. So in Seattle, you're not doing so hot with solar, but in Eastern Washington, you're in good condition. Yeah. Yeah, that's a really good point. So certainly by county, you want to know. All right. Last little bit. This is from the city's GIS. And let's look at what kind of information we have on this. So Nick, what kind of information do you see on this map? Right. And what kind of data, what kind of GIS data is that? And it's also going to be vector data, right? Because it's points connected by lines. What other types of data are in here? Justin. Yeah, so I clicked on this parcel, right? Here's a polygon. So this is the land parcel data set for the county. So all the property boundaries. And it's got a whole table of information here. Who's the owner, address, area, acres, year built, all those things. So there's a whole database connected to this. And there's a URL. I could click on this if it were live. And it would take me to the county or city tax assessor, and I get more information on that. We've got aerial imagery underneath, right? There's a polygon of the river footprints. So yeah, that's the kind of the basic stuff that we have here. Here's another data set. What does this look like to you? The little symbols. Categorical. Maybe nominal too, right? They're kind of connected. What do you think it is? That's a fist. What's that? A needle, what's a broken window? This is crime.
I was like, fisted needles. Wait, no.
What is this, Grand Theft Auto? Yeah, so this is the crime data. So anytime there's a reported crime, the police show up, they do the address, and then this is linked. So you can actually look this up and see all the fights that happened on campus. Uh-oh. And then you can click on that and say, okay, here's the address. We had some vandalism. Here's when it was reported. Here's the police report. All right. Thanks for going on that tour of mapping. So now we're going to do, let's see here. We're going to work through chapter 1. We're going to start on that.